Hi, in this video we are going to study the half wave rectifier, or we can say that we are going to study that how we can convert AC current into DC current. Now I hope you know what is AC and what is DC. Now AC current is alternating current, its wave is like this, and DC current is like this, steady current. Suppose this is the graph of DC current which have a constant voltage, but AC voltage keeps on changing at every instant of time. We can see that with time the function is changing its voltage value. Suppose this is V and this is, we can say, the theta or T, because we are representing here it as sine wave, so we can represent it that voltage is changing for every instant. Now what we have to study here is that how we can convert this AC into DC. Now in the previous videos we have learned that what is PN junction, how it is formed, what happens when it is forward bias and what happens when it is reverse bias. Now we are going to use all those concepts to convert AC into DC. Now there are many forms by which we can convert AC into DC, but the most basic form is half wave rectifier. Now what is rectifier? Anything which opposes the flow of current in one direction but allows the flow of current in the other direction is called the rectifier. Now it's a little bit confusing that what does it mean. Now take an example of PN junction. Now we all know that it allows current to flow through it when it is forward bias, but it does not allow the current to flow through it when it is reverse bias. So this is an example of a rectifier, that means PN junction is a rectifier. Now we are going to use the property of PN junction here to convert AC into DC. That means we are going to use rectifiers to convert AC into DC. Now what is half wave rectifier? Now we all know that AC current is like this. Now if I am able to convert half of this wave into DC, then that means it is half wave rectifier. That means it rectifies only the half wave of the AC current. Now let us see that how it all happens. This is the procedure of half wave rectifier. In this diagram we are showing that this is the AC input. This is the transformer which is used to step up or step down the voltage which is required in the further circuit. Now this is PN junction diode. This represents the P side, this represents the N side. This is a resistance, and this arrangement shows that we are going to take output voltage across this resistance, so we call it as load resistance. Now what happens? Let's see that how we can convert AC into DC. Now we all know that AC have this kind of structure, that means AC is alternating current. It has some positive value of voltage as well as negative value of the voltage. Now what happens? Let us see. Now this is at 0. The voltage is 0 for the AC current. We are not representing this wave, only this wave. Now AC current at 0 time has 0 voltage. As time increased, what happened? It started increasing its voltage. It remained positive until here. Then after some time it start decreasing and it start gaining negative value. So what does it mean actually? That suppose AC input is being put on here. Now I am representing one wave here. Now we can see that suppose this is 0 and this point is pi. Now at 0 to pi, alternating current had positive curve, and from pi to 2 pi it had negative curve. Now what does it mean? Now suppose this is the first half of the whole cycle. Now at first half, suppose this is the thing. So what happens here is, this is positive and this is negative. Because it has positive wave, so I will represent it like this. Now what happens? That means half wave becomes like this. That means if I made AC current into the circuit, what will happen? For this first wave, here will be positive potential and here will be negative potential. Now, because this is positive positive is here. Now what happens? This potential is given to this circuit by this transformer. Now this has been shifted here at the secondary coil of the transformer. Now what happens? We can see in this circuit, this is positive, this is negative. Now if I see this potential with respect to the diode, now positive is connected to the positive of the diode and negative is connected to the negative of the diode. That means the diode is forward biased because positive terminal is connected to the positive of the diode and negative terminal is connected to the negative of the diode. That means the diode is going to conduct. That means there will be flow of current like this. Now as the current has moved from the diode, that means it will move through the resistance also, and we can note the potential voltage across this resistance. So for this wave, we have got similar wave here. Because it is of varying voltage, we will get a varying voltage here also in our output. Now for the next half of the cycle, what happens? This is negative voltage. That means it is providing negative voltage. So automatically positive is here. Now this primary coil is going to shift this to the secondary coil of the transformer. That means now this is negative and this is positive. So we can see in this circuit, the negative terminal is connected to the positive of the diode and positive of the terminal is connected to the negative side of the diode. That means it is reverse bias, and we know that diode does not allow current to flow through it when it is reverse bias. That means we are not going to get current. If we are not going to get current for this half, then what happens? That means we can represent the output. That means no current is flowing through here. That means we are going to get no voltage across this resistance. That means for this wave, we have no voltage. Then again the second cycle starts. Now suppose this is the second cycle. When this half of the cycle comes, then again positive, here negative, here positive, here negative, again forward bias, we will get an output. Then for the next half, again reverse bias, and we are not going to get output. So what happens here? We know that alternating current is the current which have positive and negative voltage after particular cycle. But DC is a current which have positive voltage only. So here we have got an output which have positive voltage only. It does not have any negative voltage. That means this is DC. But we all know that DC is a steady current. It has this kind of graph. But here we have rectified AC to DC. But what we have got is pulsating DC output. So this is pulsating DC output. So this is how the half wave rectifier rectifies AC current to DC. Now this was the theoretical explanation. We can also derive mathematically that how we can get that how much current we are going to get here and what happens. We can see it. Now suppose the input voltage is given. Now it is E, and we know that AC voltage is kind of sine wave function, so we can represent it as this. And we know that obviously it will have some peak value, so this is the peak value represented this. Suppose this is the voltage graph, so that is the peak value and it varies according to the sine function. So this is the representation of the AC current. Now what we are getting the output. Now for output let us consider current. Now for current it is going to be, I am talking about output here. Now we know that this is resistance RL and this is a diode, and practically we have talked earlier that diode have its own resistance. Internal resistance is always there. That is why this is not an ideal diode. It is a practical diode which we have. So let its resistance be small r. So we know that according to Ohm's law, V is equals to Ri. That is, voltage and current are directly proportional to each other. So we can calculate I, that is E by R plus Rn. This is the total resistance, and we are going to get this much output of the current. We know we are going to get output only for the half cycle of AC current, that is for the positive cycle, and that positive cycle varies only from 0 to pi. When sine has values between 0 to pi, it has output, and we know that we don't get output when its value is from pi to 2 pi. For 0 to pi we have value, and for pi to 2 pi we don't have value. This is the output I, this was the input given. Now I can represent this E as Em sine of omega t from this. So we get this values. Now from this only we can get the amplitude of the current output. Let it be Im, and it is represented by Em by R plus Rn. So this is the peak value of the output current which we get. This is the peak value of the pulsating DC output. Now we all know that DC is a steady graph. It has this kind of graph. But what we have got is this. So I want to do my calculations according to this and not according to this. Because according to this graph, I have to calculate current and voltage at every instant of time. But here I know that for all time I have one value of current and one value of voltage. So I am going to reduce my calculations. How can I do it? I am going to take average of this all voltages. Now to take average of the voltage, what I have to do? I know that for a particular cycle, there are some values and those values are repeated in every other cycle. So I am going to take average of a particular cycle and divide it by the base, that for the whole cycle what I have got that average. Now let me represent it. We know that these are the output values. Now I average, or I am saying that I am converting my DC, pulsating DC to steady DC mathematically. So I can represent my I average as IDC, my DC current, and its formula is average for the one cycle. So its formula is, here I am saying it is 0, it is pi, then it is 2 pi. So we can represent here that for 0 to 2 pi, there is one cycle for 0 to 2 pi, and its value I have calculated here I. It is Im sine omega t dt. Here this is Im. So this is the value for one particular cycle. So when we integrate it, what I am going to get is that IDC. Now I can erase all this. So when I integrate whole this equation, I will get that my IDC or my I average is Im by pi. So this is the value of average DC. That average current which I am getting in my output is this. As we all know that this is DC and this is our output. So that means this DC is not particularly DC, because if it would have been DC, it should be like this, but it is like this. And we can see that these are the characteristics of AC because they are changing their values at every instant. So what we are going to do is, we are going to calculate the root mean square value of the current which is produced here. Now one thing I know that you might not be remembering is that as I calculated the average of this pulsating DC and I got some value, and I know that if there is current in a wire, suppose it is DC, then if I am going to touch the wire, I am going to feel current, and even in my calculation there is current. But what about alternating current? Now this is alternating current. Now if I am going to touch the wire which have AC current, I am going to feel current. But mathematically the average of AC current is 0. Because we can see that this curve cancels this curve cancels this. So mathematically average current is 0. So what does math says about AC current? That there is no current. But we know that if I am going to touch the wire of AC current, I am going to feel shock. So what we calculate for the AC current is RMS value, that is root mean square value for the AC current. It is nothing, it is the, as the name indicates, root mean square. So what is it? We are going to take root of what? Mean. Mean of what? The squares of the things which we want to take. So it is going to be like this. Now I am going to take root mean square of my pulsating DC. Why? Because it has some AC characteristics. So to check that, now I am going to take RMS value. And here we know that it is 0 to 2 pi. I am going to take the average for the squares. So that means here I am going to take square of my current, and I know what is the value of the current. It is Im sine omega t dt. So I am going to take square of this, and when I will integrate this all, I am going to get my RMS as Im by 2. Now from this what we can see, that this is the value of IRMS. Now this factors represents the AC characteristic of my pulsating DC output. Now next, I have said you that we are going to study the rectifiers. That means we are going to study that how we can convert our AC into DC. Now I have converted this wave to this wave. I am showing it just roughly, it's not the actual diagram. Now what happens here, that we have got some output. Now obviously whenever we get some output, we always try to check that how efficient our machine was. Now we had some circuit, it has diode, it has load resistance. Now I want to check that how efficiently my circuit has converted AC into DC. So let's check that how we are going to see efficiency of my this half wave rectifier. Now for efficiency, this is neta, this is the representation or denotation of the efficiency. This is the symbol for efficiency. Now obviously we are talking about current here, we are talking about voltage here. So how can I get the efficiency? Obviously I am going to get a comparison between the powers of my input as well as output. That means I have given some power to a person, and now I am going to check that how much of my power he has used in the perfect or the best way. So I have given power AC. I have given AC voltage. Now I am going to check the ratio of the output DC voltage to the AC voltage. So this is how I am going to check the efficiency of the half wave rectifier. So we'll put the formulas here. We know that power is equals to voltage into I, and we know that V is equals to Ri. So we can say that power is equals to Ri square. Now when I have got the output, I know the output has come after moving from diode and the load resistance, and we know that diode had internal resistance small r. So the total resistance for the output was small r plus capital R into I square, that is I am going to take the output current, that is the pulsating DC current, and here input. Now input has been taken after only Rn. We are not connecting diode at that circuit because I am just taking the measurement of my input, that how much input I have given to the circuit. So it will be here, and I have given AC current, so it will be like this. So after calculations, if I say we have got this thing, we have calculated the output DC current as average current. Now average current of the pulsating DC output was Im square here by pi. So this is the value, and we have RL here. AC we have calculated for the AC current RMS value, and RMS value was this. Now if we calculate all those things, we are going to get near about 0.40%. If I neglect these R's, near about, sorry, this is 0.40, that means efficiency of my half wave rectifier nearly comes to be the 40%. So half wave rectifier, because we all have seen that it rectifies only the half wave, so that means 50% of our input has been wasted by the half wave rectifier because it does not rectify it. And moreover, we have resistance, there is internal resistance and load resistance, so that means more input has been moved out. So we can calculate it as 40% after doing the calculation. So this is how we can calculate the average current, that is the DC output, if we want it in steady form. Now if I want to calculate the AC current, I am going to take RMS value, not the average value for AC, and we have studied the efficiency of half wave rectifier.